Welcome to this first lecture on pumping lemma. Let's have a quick look on what pumping lemma states. Pumping lemma is a property which regular languages are supposed to exhibit. So if a language is regular, and it is infinite, then there does exist a DFA, a deterministic finite automata, which represents this language having m states. So if my f part is true, then I can easily conclude that there does exist a DFA, which I didn't see, but it has to exist with m states, where m is a finite number. So if we try to visualize this kind of DFA to exist, so it will be having a start state, it will be having at least one final state, and in total there will be m states. And because of the property that it is infinite, it must have to have a loop, at least one loop, somewhere on the DFA starting from the start state going up till the final state. So if I start from the start state and I try to consume a string from the start state up to the final state, then I start from here, I pass through this entire walk, I reach to this intermediate state, I take a walk around the loop, and then I keep on moving towards the final state. So in that way, the string W which I consume, starting from the start state, going up till the final state, it belongs to the language which we are talking about. Plus, one additional thing which we know about this W is that its length will be at least m. It will be greater than or equal to m. Why? Because in total I have m states, and if my W is taking this whole walk, it's consuming the loop. If it's consuming the loop, then according to pigeonhole principle, at least one state is being repeated. So if at least one state is being repeated, I'm going up till the final state, so my total string which I would have consumed would be at least of m length. And this condition is also important to make sure that my language is infinite. So the pumping lemma states that if language is regular and infinite, then the DFA which it represents has m states. It must have to have a loop somewhere on the valid path, starting from the start state going up to the final state. We choose a W which belongs to my language, and length of the W is at least m, where m is my number of states. We sometimes also call it pumping length. Then this W can be broken down into three substrings, whom we call X, Y, Z, such that X is representing the loop which is before the loop, Y is representing the loop part, and Z is representing the post-loop part. So if I can separate my W into these three substrings, that means that I started from the start state, I consumed X, then I consumed Y at least once, which gave me the provision to repeat that state because Y is representing the loop part, and then I carry on my Z path. So in total I'm consuming X, Y, Z, which is making W. So if this whole thing is true, then length of Y individually should be at least 1, which makes sure that length I cannot have an empty loop. My loop will be consuming at least one character on its way from start to the final state. And this provision will help me to make sure that my language is infinite, because if loop is a non-empty loop, then I can repeat it any number of times to produce every time a new string. Plus, the combined length of X and Y cannot be more than m. And the reason this statement makes sense is that just imagine the opposite, that X, Y combined can be beyond n. That essentially means that my loop will be outside the DFA. It does not make any sense. So that's why we have to make sure that I cannot assume any X or Y in combined having more than m length. So pumping lemma states that if we observe and adhere to these conditions, then this XYZ can be transformed into xy power iz, and whatever So what does this mean? Y power I means that we have to repeat the y part I times. If we keep on repeating this loop, this will also belong to the language for all I which are greater than or equal to 0. So this is the fundamental definition of my, this is the fundamental property of my regular languages, that they adhere to this thing. But we cannot use this property to prove a language to be regular. Why? Because of this thing. It applies on all I's. And how many I's are there? They are infinite. So if I have to prove something to be regular, I have to show on all possible x, y, I, z's for different values of I that they adhere to the conditions of pumping lemma, and the resulting string belongs to the language. But there are infinite number of strings which I need to show, which I can't show. Though this is a property of regular languages, but I cannot use this property as it is to prove something to be regular. So part 1 of our discussion today is that if I have to prove something to be regular, I must have to come up with either a DFA or its equivalent NFA or a regular expression. So these three tools which we already know, which we are familiar with regular expressions, DFAs or NFAs, can be used to prove something to be regular. So, but understanding this pumping lemma is very important because of a fundamental reason. And the reason is that now we want to talk about the languages which are not regular. So we assume a language to be regular, if a language about whom we are not sure that whether it's regular or not regular. So if you assume that it's regular and at some point in time it gives me a contradiction on at least one I, then there will be sufficient evidence to prove that thing to be non-regular, which we'll see in different examples today. So if you have understood the content so far correctly, so I'm going to pose a very small quiz. Part 1 of the quiz is that I can take a fixed length W to run on a DFA which I didn't see. Is it true or false? So pause the video for a while, ponder upon the statement that can I take a fixed length W to run on a DFA which I didn't see? Can I do this or not? Whatever is your answer, try to figure out the reason. Why is it so? Second question is that I don't take a fixed W, but I take a fixed Y. Can I do so? Again, the question is whether it's true or false, and whatever is your answer, try to come up with the reason. So at this stage, pause the video and try to answer these two questions yourselves. So after the pause, I'll be writing the answers over here. I'll be showing you the correct answers, and if your answers match with our answers, then you can continue with the video. Otherwise, try to rewind from the start. So the answers are that if I can take a fixed length, well, I can take a fixed length W on a DFA which I didn't see. The answer is no. Why it's no? Because my pumping lemma stated that length of W should be greater than or equal to N. If I'm taking a fixed length W, then how can I make sure that it's greater than or equal to N? And what is N? I don't know because I didn't see the DFA. So then my answer of the first question is no. Because of this condition, I can't make sure that this condition is true on a fixed length W, and I can't compare that fixed length with the variable length. And what is the value of this variable? I don't know. Why I don't know? Because I didn't see the DFA. Answer of the second question, I don't take a fixed length W, but I can take a fixed loop. The answer is again no. Why? Because once I break down my W into X, Y, Z, I don't know exactly where this Y will come. It might be on the start state, might be somewhere in between, or might be on the final state. And what is the exact length of that value? I don't know. So I can't fix a Y while proving something using pumping lemma that I'm taking this particular Y on a DFA which I didn't see. So I can't assume a fixed length Y. I can't assume a fixed length. The answer of both of these questions are false. So what we are going to do next is that we're going to start with a slightly complicated example. We'll write, once we have been given that example, I will give a language that there are some number of ways such that those numbers are n squared for n is greater than or equal to 0. So, and I have to either prove or disprove that this language is regular. So part 1 is that I just need to sit back and try to ponder upon that which way I need to adopt. So my language could be regular or could not be regular. It has not even been given in my question that whether this language is regular or not regular. If somebody tells me that this is a regular language, then I can at least put my efforts in one direction. Or if someone tells me that this is an irregular language, then I can put my all efforts in another direction. And what are those directions? In the first case, the direction is that if I know prehand that this is regular, so I will not apply pumping lemma. Why I will not apply pumping lemma? Because pumping lemma's final conclusion stated that x, y to the power I, z has to belong to the language for all i's. And how many i's are there? They're infinite, so I can't take that route. So if it is regular, so I'll either be trying to draw a DFA, or I'll be drawing an MFA, or I'll try to come up with a regular expression. Versus that I have been given other information that the language is non-regular and I have to prove it. So in that case, if I know prehand through some mechanism that language is not regular, then one thing is sure, that I cannot draw a DFA, I cannot draw an NFA, and I cannot write a regular expression because all of those three tools are equivalent to each other. So that way, I'll go for applying pumping lemma on that language with the assumption that it's regular, and at some point in time, I should be able to find an I which will violate this condition. If I succeed to find one I which violates this condition, then that I will make this whole statement false. Why it will make it false? Because it has to be, if it is regular, it has to be true for all i's. And if I succeed to find one I which makes it false, then it means that the entire statement is false. So if the entire statement is false, then my assumption that I was trying to apply pumping lemma on a regular language, that assumption is not correct. So there will be sufficient evidence to prove something to be regular. So my first step given this language, that what should I do is that that's my intuition. I need to intuitively think that whether I should classify this language as regular, is it regular or not regular? And what will help me to come up with that intuition? So the only thing which can help me to come up with an intuition is that regular languages are the languages which can be possibly processed without having memory. So on my language statement, I just need to ponder upon that can I do that kind of computation without having memory? And if I succeed to convince myself that yes, I can do these kind of computations without having additional temporary memory, then that language can be categorized as regular. And my DFAs or NFAs are the memoryless machines. Or other way around is that I convince myself that there is a complicated kind of function involved in this language, and in order to make sure that that function is being adhered to, I need to remember something, and if I have to remember something, I need to have memory. So if I need memory, then language cannot be represented by DFA. So that way I'm going to go for non-regular option. Another kind of intuition which I can think of is that because n starts with 0, so 0 square is 0. So the first element which will come in my language is lambda, which will contain no a's. Next n is 1. I can have 1a, 1 square is 1. Next n is 2, so 2 square is 4, so I can have 4 a's. Next n is 3, I can have 9 a's. I can have 16 a's. I can have 25 a's. I can have 36 a's. I can have 49 a's. I can have 64 a's and so on. So if you look at the pattern, I can have 4 a's, 9 a's, 16 a's, 25 a's. So the interval is not a fixed size. If interval is not a fixed size, then probably it will be quite challenging for me to come up with a state machine. So if interval would have been of a fixed pattern, then I would have been able to, for example, if it would have been a multiple of 5, I would have been able to have jumps of 5, 5, 5, 5. And in that case, I can encode that thing in RDFA without having additional memory within this. I can encode it within the states. But this kind of variable pattern cannot be encoded within the states. So the intuition says the kind of pattern which we are supposed to adhere over here in this particular language needs memory. And my intuition says that language is not regular. So pause again here for a while, just to make sure that you are with me on the intuitive part. And what is the intuition? What was the question? The question was that given an unseen language whose additional information has not been provided to us, that whether it's regular or not regular, I have to first decide a track. And that's very important. If I decide the wrong track, I will not be able to come up with the right conclusion. So I have to ponder upon, I have to think, I have to hold, I have to pause, think and think and think, and then try to come up with an intuition that whether it's regular or not regular. And whatever is your intuition, try to follow that route. So in this kind of pattern, my intuition is saying that it is most probably non-regular because of the kind of pattern. I can't encode this kind of variable pattern in my state machine. And if you're not convinced that this kind of variable pattern, why this kind of variable pattern can not be encoded in a DFA, then you can hold over here again, pause it, ponder upon again, or rewind the video to make sure that you are convinced with the intuition. So now, because we are convinced that language is not regular, so we are trying to apply pumping lemma and we assume that this language is regular. If it is regular, then it has a DFA having n states. And where does this DFA exist? We did not see this DFA. This DFA exists because we assume that language is regular, hence there must be a DFA. And what will be the m? M will be a finite number, which we are not exactly sure about that what would that m be. So if there exists a DFA, the next step is that we choose a string, W, which belongs to this language. So the first condition which we must adhere to on the selection of the string is that it must belong to the language. The second condition which we must adhere to is that its length is greater than or equal to m. So I can choose a string by making sure that these two conditions are being fulfilled in complete sense. The first condition is that the string must belong to the language, which is very obvious. And second condition is that its length is greater than or equal to m. Why we are interested in this condition? Why its length should be greater than or equal to m? If its length is greater than or equal to m, then according to pigeonhole principle, this W must have been consuming the loop part. In order to accept this W, at least one state is being repeated. If at least one state is being repeated, then there has to be a loop which is non-empty inside the W. So I can break down this W into three substrings, which we just talked about while introducing the pumping lemma. That this W can be broken down in X, Y, Z, and the kind of W which we pick What are those XYZs? These are same which we have just talked about, that loop is non-empty and combined length of XY is less than or equal to M. What should be the exact W which we choose? We choose M square. What does this mean? This means, does this belong to the language? Yes, this belongs to the language. Why does it belong to the language? Because number of A's are square of M. What is M? M is guaranteed to be an integer. Why is it an integer? Because it is number of states. And if it's square of an integer, then it does belong to the language, because that's how my language is being defined. So the first condition is being adhered to. And what is its length? What is length of this W which we have just chosen? Its length is M square. It contains M square number of A's. And hence, the second condition is also being adhered to, that its length is at least M. So M square is greater than or equal to M. Okay? So, now, in order to understand it a little better, I just try to open it up. So what does it mean? It means that it contains so many A's inside it. What is the exact number of A's which it contains? That is M square number of A's. And according to this condition, I can break down this W into three parts. It has an X part, it has a Y part, it has a Z part. Where are these cuts being made exactly? I don't know. Why I don't know? Because what are the meanings behind X, Y, and Z? If you recall the definition of pumping lemma, which we just defined in the start of this video, Y is the loop part, X is the pre-loop part, Z is the post-loop part. So, where is Y? I don't know. Why I don't know? Because I didn't see the DFA. I just assumed that DFA has to exist somewhere. I don't even know the exact number of states in that DFA. So I assume that it has some n number of states. So whatever is the DFA, Y can be somewhere on the DFA, and it cannot be empty. So its minimum length is 1. Why it cannot be empty? Because if it is empty, then my language cannot be infinite, which is the prerequisite of applying pumping lemma. And what is the total length of X and Y? This cannot go beyond M because of the second condition which we just discussed. And just to recap, Y cannot be more than equal to M. If we allow it to be more than equal to M, that essentially means that Y part, the loop part, will be outside the DFA, will be beyond the number of states which are N. So that's why it does not make sense. That's why we have to adhere to this condition that combined length of X and Y is less than equal to M. So the total X, Y, and max, the combined length will be less than equal to M. And exactly what it is the only thing which we know is that it is somewhere between 1 and M. But we can't fix it. And this is very important. And this is the common mistake which we usually make while proving things. So please make sure that you are with me on this point, that why can't we fix it? We can only fix it if I show you the exact DFA. If you can see the DFA, then you can see here is the loop, this is Y, this is pre-loop part, this is post-loop part. But we did not see the DFA. We just assumed that DFA would happen somewhere in the word. So that's why I have to just make sure that length of Y would be somewhere between 1, it cannot be 0, and it cannot be more than M. So my combined length of X and Y will be somewhere between 1 and M. So move on. So what we do is that let's try to pump it. We go with X, Y square Z, which essentially means that we are talking about X, Y, Y, Z. If we are talking about X, Y, Y, Z, what does that mean? We already have X, Y, Z. X, Y, Z is our original string. And how many A's does it contain? It contains M square number of A's. What we are doing is that we are adding one more Y in my string. So number of A's will increase. So if I put the coordinate over here, the length of this string is equal to length of this string, what it is, it is exactly X, Y, Z had the length M square plus 1 Y has been added. So length of Y will be added into this m square. So again, the point to ponder upon or think about is that whether we are adding one y or two y's. We are adding one y, but we are writing over here two y's. Why? Because one of them has already been part of my original w. So x, yz was originally there and its length was m square. When we repeated y twice, we added only one additional y. So m square was the original length and length of one more y has been added into it. So what is this? So m square plus length of y is guaranteed to be less than equal to m square plus m. And this is the turning point. So over here, rather than putting the equal sign, I'm putting less than equal sign. Because we just got convinced over here that what would be the lower limit on y, on length of y, and what would be the upper limit on length of y. The lower limit on length of y was 1. The upper limit on length of y is m. So if m square is the same original w plus y repeated once additional time, so this m square is same. What is this? This is less than equal to m. And this is the upper stretch. I can't stretch y beyond m. So if I repeat y twice, if I come up with x, y, y, z, the maximum length which I can get is m square plus m. Now the question is, what is this? Because my language was talking about that the number of characters in my language should be scale of an integer. Is it a scale of an integer? We don't know. It's not clear. So my previous length was m square. It cannot be 0. Why? Because y has been added and length of y cannot be 0. So it has to be somewhat greater than m square plus 1. But what is the next immediate scale? If we are talking about scale of m, what is the next immediate scale? That would be m plus 1 whole scale. And what it is? It is m square plus 2m plus 1. And if we try to now relate these two entities, m square plus m and m square plus 2m, m square plus 2m plus 1, it is very obvious that this thing is clearly less than this. So if m square plus m is clearly less than with the next immediate scale, then what does it mean? It means that when you pump the length of y, the resultant length cannot approach the next immediate scale. By next immediate scale, we mean the kind of scales which we had opened up at the start of the example. So it's guaranteed that m square plus m is not a perfect scale. So hence, the resultant string, which was x square, y square, z, this does not belong to the language. If it does not belong to the language, then there is a contradiction. If such kind of violation exists, then the language is no more regular. Why? Because the entire construction of the proof which we have done so far was based on an assumption, and that assumption was that language is regular. So if that assumption would have been true, I would not have been able to find the contradiction over here. So if I've reached out a contradiction, then my assumption is wrong. The assumption was that language is regular. So hence, after having the contradiction, I can prove that my language is not regular. So that's it as far as this proof is concerned. So the last part is that if you have really understood each piece of this discussion, then that's perfectly fine. Otherwise, pause over here and try to recap this example again. But if you're okay that what is pumping lemma, then I'm going to put certain questions over here, writing down 4 kinds of languages and try to figure out whether these languages are regular or not regular. If they're regular, to prove them using a DFA, NFA or regular expression. If they're not regular, apply pumping lemma and clearly prove that those languages are not regular. The first language you're talking about is A raised to the power n cube when n is greater than or equal to 0. The second language which I am about to talk about is A, M, B, M, C to N, and n is greater than or equal to 0, and in this language alphabet is ABC. The next language which we wanted to talk about is the language in which W belongs to any possible combination of A's and B's such that number of A's in W is equal to number of B's in W. And this is not just A and B, because A and B forces us to adhere to that order. Well, here that order is no more fixed. W can be any combination in any order of A's and B's. The only thing which we have to adhere to is that number of A's are equal to number of B's. The next one is that it's AM and it's AB such that N and P are never equal. Both of them are greater than or equal to 0. So that's it as far as our pumping lemma is concerned. Try to work around these examples. They're not guaranteed to be regular or non-regular. You have to figure out yourselves through your intuition and then prove them accordingly. Thank you very much.